So it's about time for us to get started. Welcome back from break. I hope you kind of had an enjoyable time. So just before we quit for break, we had one whole lecture. We did capacitors in series and parallel. We did some combinations. So my plan today is do an example, and then do a couple of examples, talk about energy, and then hopefully get onto circuits before we finish today. Before we get started, does anybody have any questions? Okay, so we'll get going on. So I picked this example because it sort of looks hard. There's a switch in it, and you have to think about what happens in this problem. And you really have to think carefully about the physics of the problem. The algebra is not difficult, but the idea of the things that happen could be a little bit more difficult. So let's go through it step by step, and we'll think about the charge and the potential and the capacitances as we go. So it says initially the switch in the figure is in position A. Capacitors C2 and C3 are uncharged. Then we flip it to position B. So in the beginning, the switch is in contact with point A. There's no contact with point B, so nothing can happen in this branch of the circuit. This is an open circuit initially. When you have an open circuit like that, it's like that branch is not even there. Okay? So initially, the only stuff that's happening is happening in this branch. So if you wish to help you visualize it, you can say that this would be equivalent to having our battery here, our 100-volt battery, connected to capacitor C1. And this is before flipping the switch. So that's our potential delta V, that's 100 volts. It's connected to capacitor C1 with a capacitance of 12 microfarads. That switch is in place for a long time. It means that the capacitor gets fully charged up, and the potential on the capacitor is equal to the potential of the battery. Okay, so with that in place for a long time, it gets all charged up. So let's get that bit of information down. The potential across capacitor C1, delta V1, is equal to delta V, which is 100 volts. Okay, so the capacitor is all charged up. If we wanted to find the charge on this capacitor, we might call that, I think I'm just going to call it capital Q, no subscripts. That would be C1 times delta V1. So 12 times 10 to the minus 6 farads times 100 volts. Sorry, I thought I had room to write that properly. Clearly I didn't. 12 times 10 to the minus 6 farads times 100 volts gives us 1200 microcoulombs, or 1.2 times 10 to the minus 3 coulombs. Okay, so this is the beginning. This is what's happening at the start of the problem. So the next thing we do is we flip the switch. So now our switch goes from being in contact with A to in contact with B. As soon as that switch is flipped, we're no longer connected to the battery. Okay, so we flip the switch. And then our new circuit is just going to be this branch of the circuit. So we're in contact with point B. We've got capacitor C2, capacitor C3, and that's connected to capacitor C1 that looks like this. Okay, and I've left the battery out because the battery is not connected anymore, so nothing can happen with the battery part of the circuit. So now let's think about the physics of this situation. Immediately after we flip the switch, so this is before charge has time to flow. We're talking the exact point after we flip the switch. At that exact point, this capacitor is all charged up. These are uncharged. That means charge is going to start to flow off these plates and start to hit the other plates until these get charged up and they have the same amount of potential. Okay, so charge is going to flow until the potential of this one is equal to the potential of these guys. The capacitor is going to act like a battery. It's going to charge up these two. So let's make a note about that. So this one, fully charged. Acts like a battery. that battery is attached to C2 and C3. C2 and C3, you notice, hopefully, maybe, depends on how much you looked at physics over break, C2 and C3 are connected in series. So this is acting like a battery to these two capacitors connected in series. So the battery is going to, the capacitor acting like a battery is going to charge these guys up. So we know that if we have two capacitors in series, we can draw an equivalent circuit. So we'll have our C1 right here. This is the one that's doing the charging, and we know the potential and the charge on it. We've got an equivalent capacitance here. We can figure out what this is. So there's our equivalent capacitance. For capacitors connected in series, 1 over C equivalent is 1 over C2 plus 1 over C3. So 1 over 4 microfarads plus 1 over 6 microfarads. So that would be 3 over 12 plus 2 over 12, 5 over 12 microfarads. Given my age, I tend to do a fraction addition. If you guys did this on your calculator, I wouldn't care at all. Doesn't matter. So our C equivalent then is 12 microfarads divided by 5, or 2.4 microfarads. Okay, so now what we have is this fully charged capacitor acting to charge up this equivalent capacitance, which is 2.4 microfarads. So our question is, after the switch is in place for a little while, what's the charge on and the potential difference across each capacitor? So now we're going to let some time go. We're going to let the charge flow, and let's see what charge ends up on C1, what's on C2, what's on C3, and what's the potential on each of those things at the end. So there's our goal. That's what the problem is asking us to find. So let's think about what happens in the problem. So right at the beginning, as soon as the thing is flipped, capacitor C1 has charge Q, and it carries potential of 100 volts. And that Q was 1.2 times 10 to the minus 3 coulombs. What's going to happen is charge is going to leave that plate, and it's going to flow here until those two have equal potentials. Okay, so charge is going to flow. Until the potential across capacitor C1, we can call that V1, equals the potential across the equivalent capacitance, we can call that V equivalent. Okay, so charge is going to flow till those two things have the same potential, because if the potential wasn't the same, charge would keep going. So it's when potential is the same that charge is going to stop flowing. So that's one thing, those potentials are going to be the same. The next thing we know is that charge has to be conserved. Some charge is going to leave here and go over here, but the same total amount of charge is going to exist. So the total amount of charge still has to be 1.2 times 10 to the minus 3 coulombs, right? No matter how it divvies itself up, we can't change the total charge. So we'll say charge is conserved. So if charge is conserved, the net charge Q is going to be divided over the two capacitances. Q1 plus Q equivalent. So everybody okay with those ideas? I gotta say, this is the hard part of this problem, is recognizing those two bits of information. They have to have the same potential, and that the total charge has to stay the same. So this is the hard part. So let's use this in an equation, and we'll see how potential comes into play, remembering that we know the capacitance is here. So Q equals Q1 plus Q equivalent. Q is 1.2 times 10 to the minus 3 coulombs. Q1 is going to be capacitance 1 times potential 1. And our Q equivalent, the amount of charge on the equivalent capacitance, is going to be that equivalent capacitance times the potential across it. Okay, So we just put in that Q is equal to C times V for both of those capacitors. Okay, what next? Well, V1 and V equivalent are the same, so that's the same as C1 V1 plus C equivalent times V1, because those two potentials have got to be the same. So you can take your V1 inside, and now we can solve for that potential. V1 is going to be 1.2 times 10 to the minus 3 coulombs, that's our Q, divided by the capacitances added up. So C1 was 12 microfarads, C equivalent was 2.4 microfarads. That gives us a potential of 83.3 volts on each of those two capacitors. Okay, I don't really want to mess up this diagram, so I'm going to redraw my diagram down here. So we'll say after charge flows, there's my capacitance C1, there's my capacitance C equivalent. I know my C1 is 12 microfarads, I know my potential is 83.3 volts, my C equivalent, I know that that's 2.4 microfarads, and I know that that has potential 83.3 volts. Okay, so far so good. Any questions? Now we know something about the potentials and the capacitances. Now we can find the charge because Q is C times V. So let's find the charge on C1 first. So Q1 equals C1 times V1. 12 times 10 to the minus 6 farads times 83.3 volts. So the charge there is 1 times 10 to the minus 3 coulombs. So some of the charge left C1 and it flowed to the other capacitors. This is how much is left on capacitor C1. Okay, so we've got 1 out of 3 done. We know the charge and the potential on this capacitor. We're asked for the charge and the potential on all the capacitors. Next, we want to find the charge and the potential on capacitors C2 and C3. We have to remember where they came from. So let's just back up a step in our circuit. Let's remember that this was the series equivalent of C2 and C3. So here's C2, here's C3. We have to remember what we know about series equivalents. Capacitors in series have the same charge. So C2, C3, and C equivalent all have the same charge because C equivalent is the series equivalent of C2 and C3. So C equivalent, C2, C3 all have the same charge. And then I'll just use a little bit of shorthand and I'll say because series. Okay? So because it's the equivalent capacitance of a set of capacitors connected in series is what because series means. So we can find out the charge on C equivalent because we know the equivalent capacitance and the potential. So Q equivalent equals C equivalent times the potential. 2.4 times 10 to the minus 6 farads times 83.3 volts. The charge on this equivalent capacitance is 0.2 times 10 to the minus 3 coulombs. Of course, there's another way to get this charge. We said up here at the beginning that the net charge was Q1 plus Q equivalent. So Q equivalent would have been 1.2 minus 1. We could have used that equation as well. Lots of times there's more than a way to get to your answer. So we can either use this equation or this equation to get our Q equivalents. So that means this is the charge on these two capacitors. So C2 has a capacitance of 4 microfarads, charge of 0.2 times 10 to the minus 3 coulombs. C3 has a capacitance of 6 microfarads and a charge of 0.2 times 10 to the minus 3 coulombs. When you know the capacitance and the charge, you can find the potential. So V2 is C2 divided by Q2 . So 4 times 10 to the minus 6 farads. Oh my goodness, I'm sorry, that should be Q2 over C2. 0.2 times 10 to the minus 3 coulombs divided by 4 times 10 to the minus 6 farads. So this potential is 50 volts. And then V3 is Q3 over C3, 0.2 times 10 to the minus 3 coulombs, divided by 6 times 10 to the minus 6 farads, gives us a potential in this capacitor of 33.3 volts. And that makes sense because the equivalent had a potential of 83.3, so those two together would have to add up to be 83.3. That potential got split over both of them. Okay, any questions with that example? Yeah.
If we subtract 50 from 83.3 to find V3, will that be okay in a test?
Yeah, that's fine, as long as you put down your equation, right? You show where it comes from, no problem at all. Yeah, that's good. Yeah.
So these three capacitors right here, aren't they in series? Can't we say that all three of those are in series connection? So shouldn't all of them should have same charge?
Okay, so that's a good question. If the capacitors had all started completely uncharged, they would have to flow to carry the same charge when they were connected to a battery, that's true. But that's not what this situation is. This one started all charged up. So every time a charge leaves this one, it has to come over and land on this one. So we take one off of here and we put one on here. They have to have the same potential because charge is going to flow as long as there's a potential difference. So the thing that has to be the same is the potential difference. Because if it's not the same, we're going to get charge moving around. So if this one starts charged, it'll give up charge, but there's nothing to say it has to end up being the same charge. Yeah, does that make sense?
Yeah.
Yeah, that was a really good question. Okay, next bit we'll look at charge or energy storage in capacitors. So when we started capacitors, we said that they're circuit devices and they're used to store energy. Here's where we get to talking about how and where the energy is stored. I think this is a pretty interesting idea, and let's see about it. So when you think about energy storage, an easy place to think about energy storage is like in a coiled spring. Like if you're clicking your pen or if you have a slinky and you stretch it out. That energy stored is sort of easy to see because it's in the coils of the spring, it's in the tension of the spring. Electric energy, it's a little bit harder to see, like where is the energy, what stores it? Turns out the answer is the electric field stores it, which is kind of a wild idea because a lot of people say an electric field isn't even real, but it is real and it stores energy. So we're going to get into that bit next. So let's think about what's happening in our process. If we put an empty capacitor, hook it up to a battery, there's going to be a chemical reaction inside the battery. The chemical reaction is going to do work on each little bit of charge. It's going to start to move the charge. And because we're doing work on it, it gains potential energy. So that's kind of where we're going with this process. That's where the energy comes from initially. It's from the chemical reaction inside the battery. So at t equals 0, we connect a capacitor to a battery and we allow the charge to flow, and it flows because the chemicals inside the battery does work. We're going to look at what's happening some little bit of time later but before the capacitor is fully charged up. So it takes a finite amount of time to charge up. We're going to look at what happens in the middle of the process. So after we get started, but before it's fully charged, each capacitor plate is going to have charge we'll call plus Q and minus Q. So the positive plate will have a little bit of positive charge, the negative plate will have the same amount of charge, but it will be negative. And that amount of charge Q is greater than 0, but less than the net charge total Q, or the maximum charge stored on the capacitor. So for our notation, a lowercase q is sort of an intermediate q, it's part of the charge. Uppercase Q is the maximum possible charge. That's going to be the notation we're going to try and stick with. So a small amount of charge inside the battery, this little dq, is going to move towards the positive terminal. And the reason it moves is because the battery, the chemical reaction, does work. So if there's work done on the charge, the potential energy is going to increase. So the potential energy of the little charge dq increases by a small amount du. So the amount of work done increases the potential energy of the charge. This amount of charge du, so electric potential energy, is the amount of charge dq times the potential difference through which it was moved. So that's U equals Q delta V that we did in the previous chapter. This time it's just a little bit of energy is the little bit of charge times the potential difference. Okay, this delta V, we can write down how that's related to the capacitance, because now we know that potential difference is charge divided by capacitance. So that's a result we've been working with for a little while. So we've got dq, the amount of charge is Q, and the capacitance is C. So there's an expression for that little increase in potential energy. If we want to find the total energy, we have to add up all of the small increases in energy, and to add them all up, it means we take the integral. So U is the sum of all the little du's, or the integral of Q over C times dq. We're integrating with respect to the charge, so we're going from Q equals 0, that's at the beginning, until we hit our maximum charge, Q equals capital Q. So this one's a straightforward integral. So 1 over C, integral from 0 to Q, Q dq. The integral of Q dq is a power law. That's just going to be Q squared over 2. That's kind of one of the ones I figure you can do sort of right off the top of your head. That's got to be evaluated at Q and 0. Get a final relationship of the total potential energy is the maximum charge, Q squared, divided by twice the capacitance. So there's an expression for the amount of energy stored in a capacitor. Depends on the charge and the capacitance. One extra thing we can do with this expression, we can remember what we wrote down right here. So Q is equal to C times delta V. So if we put in that C is Q over delta V, we also get Q times delta V over 2. And if we put in that delta V is Q over C, we also get C delta V squared over 2. So there's the expression for the total amount of electric potential energy stored between the plates of a capacitor when it's fully charged. Okay, any questions? So let's do an energy example. So for our example, parallel plate vacuum capacitor, when it says vacuum, it means there's nothing between the plates of the capacitor. There's no dielectric, so that's what the vacuum here means. It has 8.38 joules of energy stored in it. The separation between the plates is 2.3 millimeters. If we decrease the separation, what happens to the energy storage, depending on whether or not we disconnect the battery first. So let's just draw a picture of what's happening in the first situation. We've got a battery, delta V. It's connected to the two plates of a capacitor. I'm going to exaggerate my picture a little bit here. Here's the top plate of my capacitor. Here's the lower plate of my capacitor. Here's my capacitor C. It's got a plate separation that we'll call D. So let's write down what we know. In the very beginning, the total amount of energy is 8.38 joules. The plate separation is 2.30 millimeters, or 2.3 times 10 to the minus 3 meters. The expression we just found related the potential energy to the capacitance. So it feels like the capacitance is important here. Let's go ahead and write down our expression for capacitance as well, because we think that's probably going to be important. So our previous slide told us that potential energy was Q squared over 2 times C. So our capacitance in general is A times epsilon naught divided by D. If this problem were changed to have a dielectric in it, the only thing that would change really is that C would be A times epsilon, where epsilon is a dielectric constant times epsilon naught. That's how the problem would change if we put a dielectric in, divided by the separation. Okay, so there's our foundation, there's our fundamentals. Let's go to part A. Part A says we disconnect the capacitor from the battery so that the charge on the plates remains constant. So if you take the battery off, charge can't flow anymore. Charge has to be the same. And what happens to the energy storage? So part A, and we've decreased the separation to 1.15 millimeters. So for part A, our new plate separation D primed is 1.15 millimeters. Right off the bat, I noticed that 1.15 is half of 2.3. Okay, so I'm going to work with symbols. If you were a numbers kind of person, you might do the whole thing in numbers, which is fine, but I'm going to stick with the symbols. So that's equal to D over 2. Okay, so my new separation is half of the original. My new charge is equal to the original because the battery was disconnected. Charge is not allowed to flow. Okay, so that's because the battery was disconnected. So now I'm tasked with finding my new potential energy. So my new energy, U prime, is my new charge squared divided by twice my new capacitance. So the Q primed bit is easy, that doesn't change. My capacitance I'm going to have to figure out. My new capacitance is my area times epsilon naught divided by the new separation. Okay, A epsilon naught over D primed. That new separation is half the original, so I'll put in D over 2 there. That 2 is in the denominator of a denominator, so that's the same as 2 times A epsilon naught over D. That's my original capacitance. Okay, so now I've got a relationship between the new capacitance and the old capacitance. I'll put this in here and we'll see what we get for our answer. So I've got Q squared over 2 times 2C equals 1 over 2 Q squared over 2C equals 1 over 2 times the original energy. So the original energy decreases by half, 4.19 joules. Okay, any questions? Okay, so the energy changes if you push the plates closer together. Part B. So for part B, we're doing the same thing for the plate separation. Still decreasing it by half. So same thing, decrease to 1.15. But this time the capacitor remains connected to the potential source so that the potential difference between the plates remains constant. So our new potential difference, delta V primed, is equal to our original potential difference, delta V. So this is the thing that's the same now. So if the battery stays connected, we push the plates closer together. We do have a complete circuit, so charge is allowed to flow this time. The charge can change this time. So let's see what that gives us for our energy now. U primed, we'll use one of our previous equations for the potential difference. This time I'm going to go C delta V squared over 2. I'll use this one because I know about my capacitance and I know about my potential. So I've got C primed times delta V primed squared divided by 2. So let's put our things together here. My C primed is going to behave exactly the same way as it did up here. Okay, because the thing that we did to the distance remains exactly the same. So same process as above. And my potential difference stays exactly the same. So I've got 2 times C times delta V squared over 2 equals 2 outside of C times delta V squared over 2. C delta V squared over 2 is the original energy. So this time it doubles, 16.76 joules. Okay, so the behavior matters whether you disconnect the battery first or not, because that's kind of what impacts the charge and the potential difference. Okay, questions about that example? Okay, so I just made an extra little note there that we'll be able to post with the class notes, that if you had the dielectric, the thing that changes is the capacitance by the factor of the dielectric constant. Okay, so there's our example. Now let's talk a little bit more about that energy. And we'll kind of investigate where the electric field comes into it. So the thing we just found was that the total potential energy stored between the plates of a capacitor was 1/2 times C times delta V squared, and the other expressions as well, 2Q squared over 2C, and the other one that I can't remember, CV over 2, I think. And we said that the electric potential energy was stored in the field of the capacitor. Here, because it depends on capacitance, the presence of a dielectric will make an effect. So we're going to talk about the energy with and without a dielectric. So we're going to do both cases side by side just so we see how those are different. So let's start. If we have the capacitor without a dielectric, we might say that U is 1/2 times C times delta V squared. Okay, so that's expression for potential energy in the capacitor. Let's think about C and delta V, what those two things are. Well, our capacitance C is equal to the area times epsilon naught divided by D. And let's just get specific about this for a moment. This is a two-dimensional picture of a capacitor, but really it has finite size, right? The Plates have an area A. Sorry, I don't draw the best. Maybe I should have downloaded a 3D picture. So the plates each have area A, and they're separated by distance D. Right? So the capacitors do have a physical size. They're three-dimensional structures. So there it is without a dielectric. Draw it with the dielectric too. And the potential difference between the plates, delta V, is the electric field times the distance between the plates. So when you get that separation of charge, it establishes an electric field between the plates, something like this. So there's the electric field, with and without the dielectric. Okay, so there's a potential difference across the plates because there's an electric field in between the plates. That's why there's a potential difference. And the capacitance depends on the physical structure of the capacitor. Everything good so far? Okay, so I've got C here. I'm going to plug in my C here. I've got delta V here. I'm going to plug in my EV here and get a new expression for my capacitance. So then my capacitance, or my electric potential energy stored in the capacitor is 1/2 times the capacitance, A times epsilon naught divided by D, times my potential difference squared, E times D all squared. Now I'm just going to neaten that up a little bit. So I've got 1/2 times epsilon naught. Then I've got my A in the numerator. I've got a D squared here and a D on the bottom. So I've got a D in the numerator. And I've got my electric field squared. So there's another expression for the total electric potential energy stored in the capacitor. Depends on epsilon naught, area, and D, the physical characteristics of the capacitor, and the electric field stored between the plates. This is without the dielectric. With the dielectric, we're going to use epsilon instead of epsilon naught. And we might remember here that epsilon is the dielectric constant times epsilon naught. So that's with and without the dielectric. So the next thing I might notice here is that I've got A times D and A times D, and I might ask, what does A times D mean? Okay, what's the physical meaning of the area of the plate times the distance between the plates? That's the volume between the capacitor plates, right? So A times D is the volume between the plates, but more so, A times D is the volume where the electric field exists. Okay? So the electric field is only between the plates, and that volume between the plates is A times D. So A times D equals volume between plates. And that's where the field is maintained. So the volume is important, so we're going to define a new quantity that incorporates the volume, and we're going to call that energy density. So regular density is mass over volume, charge density is charge over volume, energy density is going to be energy over volume. So that's our new concept. So we're going to define energy density. Energy density is a little u. I'm going to try and be careful with my handwriting. So a little u, which is going to be the total energy divided by the total volume, which is big U divided by the volume, which is A times D, which equals 1/2 times epsilon naught times E squared. That's without the dielectric. Or 1/2 times kappa epsilon naught times E squared with the dielectric. So to me that's kind of exciting. So it says that the amount of energy only depends on the electric field. All of a sudden the capacitor itself doesn't matter anymore because we're talking about the energy density. This is a descriptor of electric energy stored in any electric field. So if you have an electric field E, this, a half kappa epsilon naught E squared, is going to be the energy associated with it. No matter what the electric field is, it will have an energy associated with it. I think that's kind of cool. Which probably makes me kind of nerdy, but what are you going to do? Okay, any questions here? All right, so anytime you have an electric field, this is how you could find the energy density. So let's get started on an example. I think we'll have time to finish it, but we'll see for sure. So in our example, we'll do a biological example. So some cell walls in the human body have a layer of negative charge on the inside surface and positive charge on the outside surface. And then when you have that separation of charge, you get a potential difference between the outer and inner cell. I think they call that cell potentials. I'm not really up on medical physics, but that's one thing to do. So let's say that the charge density on either surface is 0.5 times 10 to the minus 3 coulombs. I had a typo here. That should be coulombs per meter squared if you downloaded the notes. I think I left off the squared. The cell wall is 5 nanometers thick, so 5 times 10 to the minus 9 meters. And the cell wall material has a dielectric constant of 5.4. We want to find the electric field between the walls, the potential difference, and we want to figure out what's the energy associated with it. So, to get started, I'll just draw a quick picture of a cell. I'll say it looks something like this, and then it has a really thin cell wall. The outside is positive, the inside is negative. If you zoomed in enough, you would come to where it looks just like the capacitors that we've been studying so far. Where the thickness, so let's write down our notes. Sigma, our charge density, is 0.5 times 10 to the minus 3 coulombs per meter squared. The separation is 5 times 10 to the minus 9 meters. And there's bunches of stuff filling up your cell. It's not just air, so it has a dielectric constant that's equal to 5.4. So there's all of our information. First thing we want is the electric field. So our electric field is sigma over epsilon. When we did our section where we found electric field between capacitor plates, we said sigma over epsilon naught. That was when we had air between the plates. We no longer have air. We have our dielectric. We have whatever biological material is in there. So that's why it's divided by epsilon at epsilon naught, because there's stuff in there. So sigma over kappa times epsilon naught. And put our numbers in. And we get an electric field of 1.05 times 10 to the 7 newtons per coulomb or volts per meter. And because it's a vector, let's say from positive to negative. Okay? Or from the outer cell to the inner cell. Pointing inwards, in other words. Okay, any questions there? Okay. So next, part B, find the potential difference. Well, our potential difference is related to our electric field because E is delta V over D. So delta V is E times D. So the potential difference we just found times the plate separation or the wall separation, 5 times 10 to the minus 9 meters. So the potential difference is 0.0523 volts. It says which is at the higher potential, and you know electric field points from positive to negative. There's our electric field. And we know that electric field points from high to low potential. So the outer wall is high potential. Okay, questions? So then the last bit, a typical cell in the human body has a volume of, another typo here, I was not at my finest when I typed up this slide, is 10 to the minus 16 cubic meters. Okay, I left out a 1 there. Find the total energy and energy density stored in the cell wall. So what we've got here, why don't we just do the energy first, and then we'll think about the energy density. So total energy is 1/2 times kappa times epsilon naught times, we'll do the energy density first, and then we'll do the energy. 1/2 times kappa times epsilon naught times E squared. When we put our numbers in there, we get 2,634 joules per cubic meter. Okay, so we've got a high energy density there. And now we want the energy. So the total energy is going to be the energy density times the volume of the cell wall. Okay, so the energy density, we just used our equation. The next thing we remember is that energy density is the energy divided by the volume. So to get the energy, we'll do the density times the volume. This becomes sort of a geometry problem. What's the volume of the cell wall? So this is kind of interesting. We probably won't be able to write it all down, but I'll give you the idea. So it says treat the cell like it's a sphere. So there's the radius of the cell. And then the thickness of the wall we call D. The volume of the cell is 10 to the minus 16 meters cubed. Volume of the cell, if we're treating it like a sphere, would be 4/3 times pi times r of the cell cubed. Okay, so you can find the radius of the cell. 2.87941 times 10 to the minus 6 meters. There's the radius of the cell. If we want the volume of the wall, it's going to be this outside sphere. Subtract this inside sphere. Does that make sense? So to get the volume of the wall, you take the big one and you subtract out the little one. So there's the wall right there. So that would be minus 4/3 pi r cell minus D. So the volume of the wall is 5.1984 times 10 to the minus 19 meters cubed. So the volume of the wall is really small compared to the cell. That makes sense. They're very thin walls. And then the total energy, if we do the density times the volume of the wall, 1.37 times 10 to the minus 15 joules. Okay, which takes us pretty much right up to time. Are there any questions? Okay, today is my day that I have to run to the education building for another class, so I can't stick around for questions. I do have office hours this afternoon.